All right. Thank you for everybody that's joining us today. We're doing a presentation on understanding building systems and how moisture gets into buildings. Chris Dawkins is one of the vice presidents for the IIBEC executive board. He will be president, in 2 years, right,
2
Chris?
years, yeah,
Yeah.
2 years, yes.
He's worked in small, large, and medium-sized companies in the building enclosure, and has just been a fantastic resource for all the student programs that we've done over the last 2 years, I believe it is. Does that sound right? And
Yes.
Chris wants to kind of give you all a little bit of an introduction into the building enclosure through his presentation. Feel free at any point if you want to send something to the chat about something that's being presented, and I'll try to make sure Chris covers it. Chris will be doing Q&A at the end as well. So, Chris, you want to go ahead and
Yeah,
start the
sure.
presentation?
Rick, so my screen says this meeting is being recorded right over the top of my slide. Is that coming from your screen or mine? I'm not seeing it on the screen. I'm seeing it on my.
Yeah, I don't see it. It just has a little button up at the top that says recording right now for me.
Yeah. I'm trying to get it. Let me see what happens when I go to the next slide. Yeah, that's locked me out. It won't let me go to got it. That's it's like not like what I'm seeing on my 51-inch screen is not what I'm seeing
yeah.
on my computer. Okay. What are you seeing now? You
I
seeing,
see all your slides and
okay.
the
All
one
right, here we
slide.
go. Well, let me hold on. Let me do, it's weird. I can't, let's see. Let me try. Well, and when I did that, it went away. Okay, here we go. No, damn it. Showing. It's like got a screen right in front of my screen. But that's all right. If y'all aren't seeing it, I can live with it.
Yeah, can you
I can see,
progress from that?
I can progress. Yeah.
Okay, there we go.
Okay. So welcome everybody. This is understanding building systems and how moisture gets into buildings. My name is Chris Dawkins. You can see my credential there, and my building partner or my business partner is Wade Anderson. We've worked on this presentation probably over a 10-year period. We've presented it to quite a few building science type people, industrial hygienists, and this is the newest version. As of you're watching the newest version updated today. So we're going to talk briefly about how water causes damage to buildings. It's very, it's problematic for an owner to have water in their building. Sometimes it leads to litigation. So this is like a School of Hard Knocks presentation, and I'm sure architecture and building science students, I'm sure that's got to be in your curriculum somewhere. This is more what happens out here in the wide world. So we're not going to talk about release, but I thought I'd put it in because sometimes if you're dealing with damage issues such as mold or damaged finishes and some of the things that we have to do in addition to being engineers or architects or enclosure consultants, you on occasion have a flood and you got to help them work with others on the team, such as hygienists and restoration people, on getting things dried out and or replaced. So that's why I put release from plumbing, plumbing leaks or some kind of surface water outside the building leak. The building code says, hey, grade. This is, I know we got some Canadian folks there. I don't know your code like I should, but here in the States, grade is typically 6 inches below floor level and then sloped about 6 inches and 10 feet away from the building. That's what code should be. Certainly there's times that's not possible. So we're going to really talk mostly about bulk water, uncontrolled intrusion, and generation from airflow and vapor drive more. And you guys are smart enough to know you can print your screen, or you can print every screen if you'd like. So anyway, we're going to mainly talk about bulk water and airflow issues. But don't forget the release or flood might cause a problem. So here's some bulk water is what that's used a lot. I sometimes call it free water. I may do that during this presentation. I've tried to adjust my language over the years. Free water, bulk water is basically liquid water. And that's coming through a waterproofing assembly or an assembly that's not waterproofed. Unconditioned air is carrying moisture in the water that then, if it hits the right, the wrong surface inside a cavity, it can lead to condensation. And those are the two big things we're going to cover today. The third mode of uncontrolled leakage is diffusion. And in short, diffusion is basically moisture migrating from one side of the material to the other. I've got some nice slides coming up later that cover diffusion. But bulk water is pretty easy, but it could be multiple sources, which sometimes makes it complex. Air is a little bit more complex. And then diffusion is getting super complex. If you've got a situation where diffusion is the cause, you're probably doing some modeling and some testing. You're doing a lot of things. So anyway, so you need to understand, vapor diffusion through a material in addition to bulk and airflow. We're going to talk about, because we're focused on bulk water and air, we're going to talk about the barriers to those. So often we refer to the waterproofing on a wall, but don't forget a roof. A roof is pure waterproofing, at the exterior. So, but basically a barrier inside a wall cavity is often referred to in the industry as a WRB, and that is that water resistant or weather resistant? I don't think it matters, but you're going to hear that WRB a lot. If you when you go to the BES later in Orlando, if you go to our convention, you're at a technical talk anywhere at IIBEC or anywhere else, you're going to hear about air barriers and you're going to hear about the WRB. So there's one is stopping air. One is stopping water, bulk water, and then sometimes down here in the Southeast, they're often the same material, such as a Tyvek. A Tyvek is an air barrier because it's taped at its joints, and all of its laps. It's fully taped to keep air from getting past the Tyvek, but then that is also the water resistant barrier too. So. This is the only release slide I've got, but it's a great screenshot if you want to know how to properly waterproof, say, a tub or a shower. Very nice deal. All of the principles apply here as this is a good slide in terms of continuity of the waterproofing, the various waterproofing materials. So anyway, fundamentals. Gravity always prevails. Bulk water flows downhill. That's not hard, is it? But then capillary action can cause water to wick upward. Elevated wind speeds can make water, say in a wind-driven rain, blow up a wall. And a rule of thumb that's based on physics is that a 50-mile-an-hour wind can actually blow water. If you got a 50-mile-an-hour wind and some rain coming, typically that's a nice thunderstorm, it can actually blow water up the wall 2 inches. Many of our buildings are designed for 90 miles an hour wind speed, and then down on the coasts, as high as 140. So imagine how much water can blow up a wall during say a hurricane or a catastrophic event. So you've got to think about water, say, blowing up under a vertical flashing and possibly getting behind the waterproofing that you think the flashing is covering. So that's something to think about. Then, of course, debris. at within a roof valley or ponded, that's debris that causes a pond either on a roof or typically on a roof is also problematic. So, and then the last one I put there, slow drainage increases the probability of leakage. If you've got a very low slope roof, we're going to talk about that in a minute. If water is allowed to pond, it has the likelihood of migrating through lap seams or something like that can cause issues. So those are just some nice fundamentals. Here's a brief overview of roofs. Steep slopes, typically more 212 pitch, and that covers, I've got them all listed there. Shingles, I put metal R panels because that's typically the R panel roof is what you typically see on lower budget metal panels roofs. Higher end roofs that are metal or standing seam, that's my preferable metal roof if my client can afford it, because there's no exposed fasteners. Wood shakes, cedar shakes, cedar shingles. There's differences in those. There is actually a cedar shingle and there's a cedar shake, and that's based on the dimensions of the wood material, slate, clay tile. I may have left something out. Low slope is going to be basically 212 pitch to a 1/4 pitch. And that's, y'all probably don't see built up roofs as much as you used to. There may be some folks out there still doing built up. It's sort of been overcome by modified bitumen, which is used in modified bitumen cap and base sheet systems are used in many institutional settings. Some private owners still like them. Single membrane is definitely the most popular in today's market. And there's 3 examples of, EPDM, PVC, and TPO. I think TPO is probably the most prevalent of those 3, although the other 2 have similar properties and performance. Spray polyurethane foam, probably you don't see that quite as much, but you still run into it on occasion. And of course, metal panels are often, I've seen metal panels often in 1/4 inch and 12 pitch, or maybe 1/4 inch to 1 to 12 pitch, which would still be a low slope roof. So you see them both in steep and low slope assemblies, particularly standing seam when you get to low slope. But once in a blue moon, you'll see a 112 pitch R panels. So anyway, that gives you a quick overview. A brief, fast summary of roof flashings. I'm trying to give you terms. Base flashing is basically a membrane that extends from the roof up the wall and integrates with the wall waterproofing. So it's the vertical side, say, of a parapet wall, or a wall that abuts a roof. And then, of course, a base, I guess, based on this definition, a step flashing along a roof to wall on a steep slope roof, the step flashing that goes up the sidewall, or the rake wall, if you want to call it that, would be also a base flashing. Cap flashings typically is a metal flashing. It might be tile over the top of a parapet wall, or if you got a wall that abuts with the roof, whatever's above that wall is sort of the cap flashing material. So we may refer to those as we go forward too. Failure modes. And what I'm referring to here is failure modes that essentially cause leakage. But sometimes you have a client that goes, hey, my roof's failing. Why? Defective installation. This could apply also to low slope roofs. Probably ought to call it roof failure modes rather than just shingles roof. But I'm kind of covering shingles here at the beginning and low slope a little bit later. So basically defective installation, it could be the offsets of the shingles side to side is wrong, which sets up leaks. Defective penetrations, inadequate flashings. I've got photos coming of some of these things. Ice dams, I know Mac is probably going to see those up in Ohio State. You can see those, and James in Nova Scotia definitely deal with ice dams, which create damming on the roof. And then, of course, down here in the southeast where I am, we don't fight ice dams, but we do fight the symptoms of ice dams, and that's debris dams. You know, you get a bunch of pine needles or leaves stuck in a roof valley or up against a wall that create a dam that backs water up to places it wasn't intended to be. So that's very fast. Here's a photo of a shingle system. We were studying these apartment roofs, trying to determine causes of leakage. That's why we were there. So there's your typical apartment roof. Let's see I hope I'm not being too remedial here, but this is a ridge, of course. This is a valley. Here's a valley right here. There's a valley right there. This is referred to, the leading edge that's sloped is referred to as the rake edge. And then the lower edge is typically called an eave, which I'll sometimes just call the roof edge. And then rake is this guy. And of course, you can see in this photo, you've got a lot of penetrations that you need to think about. Anytime there's a penetration into a wall or a roof or a waterproofing that's underneath a floor system, those penetrations have to be thought about for both bulk water. On roofs, not so much air, but any penetration in a wall has to be thought about, has to be considered for its air leakage. So got some things coming. I put this photo in because essentially this is a key place. This is a roof to wall termination. You can see down at the lower end of the slope, there's like a dam created in this photo by the edge trim that sticks out. And in Ohio, I know we got folks from Ohio and Nova Scotia. You could never, this is taken here in Atlanta, Georgia. You could never get away with taking the siding that close to the roofing in northern climates, because basically you might get some ice build up at where the roof and the wall cladding meet, and which would cause serious breakage of the cladding. So you can tell where this was taken basically by what you see here. But that's why is this bad in Georgia? There's go to Hardy Plank or Nichiha or whoever the manufacturer of this cementitious siding is, and they'll tell you it should be, I think, a minimum of 2 inches off of the roof line. So we should be able to be looking at step flashing. Whoops, I jumped ahead accidentally. So the manufacturers tell you not to do it. The reason this is a problem here in Georgia is basically pine needles and leaves can get stuck in that little tight spot and then dam water, up the hill and cause leakage into those locations. So anyway, that's a fast. I think this is a really key. Anything I have in here for a reason. Diverter flashings are basically where you've got a rake edge that is adjacent to a wall, and then of course you're looking at the lower edge. Let me get there we go. So here's our lower edge right here. Here's our rake edge going up the hill. This is a really nice drawing. You can see the step flashing. You can see the wall wrap is shingled over the step flashing. The step flashing is integrated with the shingles. And then down at the very bottom of the hill, we have what's called a kick out. That's what the roofers often call it, a kick out flashing, and or a diverter flashing. This issue is a tremendous, the lack thereof, improperly installed diverter, no diverter, a diverter that was made with snips. So you have a bunch of cuts in it and they fold it up so it looks really pretty, but it's got a bunch of cuts in it. Any number of reasons diverter flashings essentially, or lack thereof, can lead to water, mostly lack thereof, right? Can lead to water basically running into the wall at the bottom of the hill. So very important thing, very important concept to understand, both for steep slope roofing, but you have kick out and diverters on commercial roofing all the time. So really, you need to really understand this concept. And if you have a question about it later, we can remember this is slide 12. We'll come back to it. Valleys, water is diverted, essentially directed is a better word, directed to valleys by the slopes. You can see on this valley there'd been a prior repair. You can see on the valley that's farther back, there's prior repair on that. So obviously at this location, this owner was having some super difficulties with their valleys. I'm going to fly through the next few slides. These are nice slides on how to properly flash a valley. The one at the left is where the shingles are going. Essentially, there's two different ways to do shingles at a valley. This is showing a weaved pattern, but what I want you to know, you can see the boards and valley flashing on top of the boards. And you can see the underlayment paper and then the shingles. That's a nice view. And then often in say shakes or some shingle roofs, shakes, slate, you often have in the lower right photo, you can see this red, that might be a copper or stainless steel metal flashing that's in the valley. So these are both two really good photos of how valleys should be done. Penetrations is a huge issue. The photo at the top left is a photo of what happens on many shingle roofs. There should be, I'm gonna keep my mouse handy here. So essentially this shingle layer to the left and right of this vent boot should be lapped over the top of the vent boot, because basically a wind-driven rain is going to blow water under the vent boot and into the hole that the vent pipe here is going through. And you can see we've got two issues at this one. We were studying why is this building leaking? Well, I was like, well, somebody's been caulking, heavily caulking the boot, the rubber boot to vent penetration, and then the flange of the boot was not properly covered by shingles at the time of its installation. So you might be getting water in two places. The bottom photo, I'm hoping you can see pretty big. Vent boots don't last forever. This vent boot had rotted away from just normal aging. So that's a hole in the roof, just following the vent pipe right into the attic space below. So anyway, penetrations matter. And then of course, I was talking to you about basics on top. This next slide is showing you can screenshot it and look at it later. Is basically showing the proper sequence and methodology for installing the vent boot so it integrates properly with the underlayment paper, the shingles, and how it should be done, a step by step. Very nice little slide there. A drip edge flashing. This is nice because we're looking at, you got a drip edge at the rake. Remember, the rake is the sloped edge. And then the lower edge is a drip edge. So you're just basically showing you how a drip edge should be integrated with the underlayment, the roofing felt in this photo. So anyway, great photos to understand, what flashings are and how they should be integrated with the roofing material. So now let's talk brief. No, that was all on shingles. That's all you get today on shingles. Low slope roof. You'll have expansion. I've got photos of this coming. A gravel stop is basically the drip edge at the outer edge of a roof, but remember, low slope roofs may be almost flat, so you'll get some expansion or contraction of the gravel stop and the roof material. Sometimes the gravel stop's typically made of metal. The roofing material is either probably adhered to that metal. So if the metal's moving at one rate, the roofing's moving at another, and that's not been properly thought through by the manufacturer or the designer, we might have a leak right there. Ponding, that's kind of obvious. Roof drains have got to be sized properly for, you know, for the rain load that they're going to see. I've seen some failures, which is a little off point, but never put an insert in a drain and say make a 6-inch drain into a 4-inch drain. You're going to do two things. You're going to put more ponding on the roof, which is a leakage issue, but it's also a load issue. It's going to overload the structure and may lead to a collapse of the roof. Improper flashings, that's similar to some of the stuff we talked in shingles. I've got some good photos of that. Failure of the membrane system, yeah, it happens once in a while. Mainly from age these days, but in past lives, they've had material failures, just the entire roof just shattered because of some material properties. And don't forget, similar to what we were talking about the diverter a minute ago, it might not be the roof, it might be the wall to roof, you know, so we're going to talk about that some with some photos going forward. This is a gravel ballasted low slope roof. I think it might be modified bitumen cap sheets. It doesn't matter. You know, for purposes of our study today, you will see ballasted roofs. A lot of times you'll see unballasted roofs, but ballast is basically a gravel, goes on top. It's a great material for both doing two things. It basically limits the UV, the ultraviolet light exposure to the roof, which, you know, lengthens the life of the roof material under the ballast. And in hail prone areas, it also, you know, helps shatter the hail and make, you know, make its force spread faster and limit damage from hail. So anyway, what I like about this picture, why I have it in the photos, one, it's showing you a low slope roof with some gravel ballast, but you can see there's a drain right here at this arrow. There's a vent assembly here. We talked about base flashing a minute ago. That's right here where the roof and the wall meet. But if we were fighting a leak here, if we were fighting a leak under this roof, we would need to know what's going on below this roof area. But we also might see that, you know, there's holes in the wall. We need to know how this louver is flashed. We need to know how the base flashing coming to the wall is flashed. Is it properly integrated? So sometimes leaks are not from the roof, they're from the wall above the roof, but down below they look like a roof leak. So I could tell you war stories if I have time for. I'll add those later so that we stay on point. This is how the base flashing, you can see is set. Whoops, doggone it. And when I grab my, hold on. So this is the base flashing at the roof perimeter wall. And so you can see my roofing is here. There's the gravel ballast. And then this is the base material or base flashing material. That happens to be modified bitumen cap sheet, tarred at this seam, or, you know, sealed in some form at this seam. Then there's a flashing on top of that modified bitumen right here. And you would presume that flashing is integrated properly with a weep assembly at the base of this hard coat stucco wall that's right here. So,
Chris, and
yes, sir.
You were saying that would go up higher in climates that they expect high winds, like Miami grade, you know, that kind of thing.
And that's usually more at the cap, but that could still apply here. Yeah, if this, I mean, you've got to, and how all this is integrated behind that metal that's right here, how that's all integrated should accommodate, you know, water blowing up the wall. But if for just a moment, pretend that hard coat stucco isn't there, and that's the vertical leg of a cap flashing. In other words, where the stucco is would be horizontal, you know, basically it would turn 90 degrees. That would be a tremendous photo to show you that wind could blow water up under this flashing probably 2 to 4 inches. At 90 miles an hour, it's probably about 4 inches. So that's got to be thought out, because sometimes you'll go on jobs and there's this flashing detail to the base flashing, basically the metal flashing to the base flashing. Termination is not caulked, which allows free water just to go right under there. It's also, think about it, the caulk is doing two things there. If it's there, it's stopping water from going up under it. It's also stopping air from going under it. We're going to talk about air a lot more going forward. So it basically created an air barrier and a water barrier. But what happens on a lot of jobs is you go out, there's no caulk there, and you can see that the base flashing is terminated about a ½ inch above the vertical. So the vertical, is it covering it? Yes. Is it covering it well? No, because it's only a ½ inch of cover, even though that's a 4 inch or 3 inch vertical leg. So it happens all the time that you go, well, here's one of your leaks right here. So that was a great question.
Yeah, and Chris, the metal cable we see going through there, is that part of the lightning protection system?
That is. That's just something that's on the roof. Yeah.
Okay.
Y'all are paying close attention. I love it. So this is just classic ponding. Ponding's never good. It's not good for, I mentioned, it could create a structural overload. But it's going to create the probability that the water is just going to sit there and then maybe migrate through a lap seam in the roofing system. It's not good. Ponding's never good. Expeditious, you want everything to expeditiously flow to wherever the exit point is. In this case, there's a drain right there. If you can see that, this water is not making it to the drain. So I don't have the word cricket in here, but that's how you basically add some triangular foam pieces to create crickets to make sure water gets to drains. That's beyond the scope of today, but Google cricket and you'll learn a lot. Plug drain, that's never good. That might be the reason for the pond in this case, or it might just be another issue where we're overloading the drain that's down the roof a ways. Holes, they're always easy, but is that a source of leak? Yeah, absolutely. This is an interesting photo. I took this in Augusta, Georgia, about 15 years ago, and I like it in this presentation. You can see basically here's the base flashing coming up the wall, right? Coming up the curb. But it stops. Do you see how it stops right at the edge of the curb? And then you can see this vent that had blown off the curb. This was a storm. I was helping the client, scope their storm damage. So we're up there seeing this right after a storm. And I was like, well, it's an interesting photo for a lot of reasons. One, the vent needs to be properly done, but whoever did the roof did it wrong. That roofing should have been lapped fully into the curb, into and over inside the curb. And then you can see how this is a nice photo for a lot of reasons. So you can see how poor the conduit to the vent was here. That's a leak. Think about that water leaking. That water would leak through that, and it would run right behind the membrane right here. But then you also have, this is something you got to think about when you're looking at water leakage. The leak might be this. It might be this electrical box. You know what I mean? I mean, if this conduit's all screwed up and deteriorated, and its termination with the electrical box is not properly waterproof, done so that it's watertight, then we might be getting water through this vertical conduit, and it might not be the vent. In this case, it was probably all of the above. But this should be wrapped fully into the curb and over the curb, and then this detail should have been properly done. And of course, this is like a maintenance issue. I hope it was watertight at the time of the roof installation, but got to be thinking about all these things. This is a pitch pocket. This is often how you how do we get pipes and stuff through the roof? Well, that's what you do it with a pitch pocket often. So sometimes you'll see pitch pockets with 4 or 5 pipes in them. And basically you fill this with a tar or pitch. That's why they're called pitch pockets. And then the roof is basically waterproofed over and into the pitch pocket. Then you fill this with a tar material, and then that keeps water out. What happens because these pitch pockets have not been maintained, you can see somebody's been up here and caulking. They know it's coming through this electrical conduit here, but you can see this pipe penetration. I don't know if you can see the opening there. So water is entering this little opening here and running behind the caulk and just bypassing the pitch and the pitch pocket. So these are all photos that are showing you problems, but I'm hoping you're understanding the concepts as we go. So here's a roof drain. That's a secondary drain beside it. This typical ponding. This is more of a TPO or PVC roof. But you see, if I pond water in this vicinity, I'm basically putting a water load on my lap seam. That's a welded seam, should work fine, but it's not designed to be a swimming pool. It's designed to be a roof that sheds water. So your lap seams are in any system are important, whether that be the built-ups are a tarred seam, the modified bitumen is adhered with, either a torch applied adhesive or a torch. The torch basically gets the adhesive that's built into the system hot so that the lap above laps to the bottom, or it might have been tarred or cold adhesive here. This happens to be a rubberized system where this is a welded seam. You can see the seam going this way and a seam going that way. Ponding's terrible. Don't do it. It's closer view, so you can see, now you see a little bit better view of how the ponded water is just sitting on top of that lap seam, waiting for a little hole into the building. This is another view of some ponding. You can tell I just love to talk about it. So, I like this photo because it's showing a lot of ponding that should raise red flags for several reasons. But you're also able to see here's your base flashing, which happens to be the same material. Turn up the wall. This is your cap flashing. I put this in because it showed a lot of features, of the roof. But ponding in and of itself is a leakage probability source, but it's also a roof structure overload condition, because the roof, in this case, this roof I know was not designed to hold water. Roofs are not swimming pools, right? So if we put a load, and you guys are building science, engineering, architecture majors, I'm guessing you should know, and water weighs 5 pounds per square foot per inch. So if we get 4 inches of water on a roof, we've got 20 pounds per square foot of additional load on the roof, which is typically the live load that the structure is designed for. If we hold water on a roof, we're going to create basically a possible catastrophic failure of the structure. And that's a whole nother subject, but that needs to keep that in mind. It's not good from a leakage standpoint. It's also a life safety issue for structural conditions, because it can lead to collapses. This is I left this photo in. You see there's a pitch pocket right here. You can see, so this was a case I looked at probably about 6 months ago, maybe 9 months ago. So this is a photo from one of my jobs. So my job was to help them figure out where the leakage was coming from. They said, we got roof leaks. And I got up there and said, well, yeah, there's a leak coming from the roof, but it's not the roof. It's this metal to metal joint right here. That's a closer view of my last slide. It looks like water down the leaf. You got ceiling, you got ceiling stains and whatnot, but it's not the roof. It's the assemblies on the roof. You can see that metal to metal joint's awful, and somebody knows it. I went to look at it as an independent consultant, like somebody knows about this. So anyway, I thought this was not a high water mark, but close to a high water mark of like, wow, look at all those vents that are just cutting holes into the sloped roof. This is a combination low slope and then steep slope. And then somebody was like, we got to put these vents somewhere. So they cut them into the roof. And like I say, not a high water mark for the worst I've ever seen, but getting kind of close. Bad ideas. And you can see that the prior people they know it. They know they've got a mess here. They're caulking the dickens out of this metal to metal joint. They're recaulking this flashing detail at the roof. There's a lot in these photos. That's atrocious. So anyway, but this was a real job where I was like, hey, would you help us figure out what's going on up there? I was like, yeah, you got some serious problems. Here's a place where you got a brick veneer or a mass masonry. It doesn't matter whether it's a mass masonry, solid brick, or a veneer over, say, a wood frame. It doesn't matter. The brick and the mortar are porous. So water is basically going to penetrate that brick and essentially bypass right behind this, edge flashing right here. So looks like a roof leak down below. It's not a roof leak. It's a flashing leak at the wall. There should have been a weep system here. This actually should have been, y'all write down BIA.org, and there may be a Canadian BIA out there, but it's Brick Industry Association. They've got tremendous technical sheets you can look up. You can go, there's about 28 or 30 technical sheets on how to properly flash virtually any condition. Tremendous technical resource. But anyway, so I was like, well, that's a problem, and then you see there's a little minor ridge repair there. Actually, there's a lot here. I'll just fast cover it. See how the ridge caps are different color than the field shingles. So I was like, they've been working up here. They've been studying. Somebody knows what's going on at this place. You can see this was sort of greatest hits kind of place. So here's some more base flashing, the metal flashing tying. Basically, this was basically tying the steep slope roof to the low slope roof below. But we've got some issues right here at this time. You've got rotted wood here. Remember, Nova Scotia and Ohio would not have done this. This would have lasted a one winter in Ohio or Nova Scotia. They got away with it here in this was in Aiken, South Carolina, I believe. So anyway, they get away with it here in the South, but nonetheless, it's still rotted. So it's not worked. Now, this is another good photo. I'd rather you not think too hard about this is brick and this is roofing. I'd rather you think this is wall cladding and this is roofing, because every wall cladding typically needs a weep. This happens to be brick, which is porous, but see the weeps are either not there at all or they're covered up by this flashing. This step flashing, that's not even step flashing, it's some kind of counter flashing. It's been put outside the brick and then caulked at its top. That flashing should not look like that. It should be basically following, it should be following the mortar joints in this case where there are weeps. And so the water would weep and then fall onto the proper flashing and then be directed to the roof. So this was one of those places. Everybody, hey, we got a leak in this hallway. I was like, so you get up there and go, well, I can see why. But for today, I want y'all that could be any siding. This could be any roofing. I want you to grasp the concept of protecting the top of the wall, regardless of what cladding is on it, and properly integrating the cladding with the roofing. So this is what the top of that wall looked like. No cap flashing. This is a porous material, and you can see somebody knows that because they've been trying to tar it up and hope that'll keep water out. But anyway, hopefully I'm driving the point home. So when you're out looking at jobs, here's some tools. They're tremendous tools. You'll use some non-intrusive meters. They're intrusive meters that have pinprick or probe into. But of course, if you're going to use those, you've got to fix the holes you make with the probes. And I've got a nice statement at the bottom. Use these with discretion, and you need to understand before these are great tools in the field, which they are. They're tremendous tools. You must do some cutting, or maybe have a building engineer that knows the building to explain the system that under them, because if you be picking up something under the material that looks like water that isn't. There might be a metal flashing right under this modified bit that looks like water, and you can see his meter. This meter is pegging, by the way. You can see that's pegging. Well, doggone it. If there's metal behind that, it looks like water, but it's metal. So I guess I've seen false negatives over the years, and I've seen false positives because, whoever was using the non-intrusive meter did not know what was under the meter, and therefore said, "Oh, the meter's calling it wet here." And we do a cut and go, "Well, it's dry." So anyway, just great tools. The point I'm trying to drive home is you must know what's under them for them to help you. This is right here. This guy taking a photo with an infrared camera. The same really applies to the infrared camera. They've got to be taken at the right time of day, so that they're not getting you got to take them when all the materials are cool, so you're not getting all the heat, heat reading from just basically being out in the sun. So same thing applies. You need to know what's under it. And then you need to make sure you follow proper protocols for time of day and, in the shade and all that kind of stuff. I've got some great photos coming up of some infrared work we did years ago that I think will drive this home point better. But just be aware of that. Let's talk about walls for a little bit. Why is building enclosure industry big today and it wasn't a long time ago? This sums it up in one slide. In the 1800s, I think this would apply to basically all locales of North America. We built quite a few buildings with mass masonry. So water would, soak in to the mass masonry and evaporate out. Also walls, window openings and whatnot were not airtight. So there was plenty of air movement from inside out. It was definitely not energy efficient, but it sure helped water management. But basically you had a mass masonry in the 1930s that, narrowed it down a little bit to a double wythe system. The term, you should know this term, wythe, W-Y-T-E-T-H-E, W-Y-T-H-E, wythe. That's basically a thickness of brick. So a 2 wythe assembly would be 2 bricks. I've looked at 4 to 6 wythe walls that are obviously old. This is what we deal with more today. This could be a steel stud or a wood stud with a wall sheathing, on the outside of the stud, some form of airspace, and then a wall cladding. So essentially the newer assemblies are lighter. They have less mass to store water. Think about how much mass how much sponge you had in a mass masonry, say 6 to 4 wythe wall. You could store a lot of water in that, and then it would evaporate out after the rain stopped. And then the other big issue, the other 2 big issues are, well, there's 3. Highly insulated. So basically we insulate the wall now. Back in the day, we didn't. So with an insulated wall, we got variable temperatures on each side of the wall assembly, which can create some condensation issues that we're going to talk about some more. Just think of gypsum wallboard, drywall. has a paper face, so it's got an organic material that mold loves to eat when it's wet. And then, of course, vapor barriers are put in the assembly. And I meant to add one more thing, and that's HVAC systems. I should add that to your notes. An HVAC system is, cooling inside or warming inside, and outside is the opposite temperature, and you can get some amazing air and vapor-borne air issues, which that's about what that segues into what we're going into now. So here's how water gets in the building. It gets in via liquid. We've talked about that, bulk water. And then air infiltration. This is sort of a repeat of a slide I gave you at the beginning, but I put this in for repetition repetition reasons, because once you start capturing, we got liquid water, we got air infiltration, and we got vapor diffusion. So we're going to cover those as we go. We're going to talk about walls, but I really want you to think, an attic space is a wall, is a cavity, right? A wall, a wall made out of 2x materials, 2x8s, 2x6s, 2x4s, like the one we just looked at in the slide about 3 slides ago. That's a cavity, right? So don't get stuck just on walls while we're talking right now about walls. So we got a WRB, a drainage space on the exterior of the WRB, which forms the drainage plane. Then at the base of that drainage plane, there should be some form of flashing that directs the water to the exterior. We'll talk in a second about air barriers. If they're different, there may be an air barrier or a vapor retarder that is separate from the air barrier. Here in the Southeast, the drainage plane is formed by the air barrier and the vapor retarder. They're all the same material. But this next slide is a brick. But remember what I told you earlier. This could be anti-cladding. This could be hard coat stucco. It could be some kind of panel system. It could be cementitious siding. The fundamentals of this are the same. We basically have a vapor barrier here, a building wrap, number 30 felt paper, which shingles properly over a flashing assembly that then weeps water to the exterior of the cladding. This happens to be brick. And then we have, of course, a wall sheathing over studs, an insulated wall cavity. And in this case, we might have, let's see, there's one for a northern climate and there's one for a southern climate coming. Let's wait till then when we discuss that. So basically that's this material right here is stopping air and water. In this case, they've got a second one. This is probably for a more northern climate in this particular concept drawing. So this is another view isometrically. Here's our WRB. Here's a flashing. This happens to be in a block assembly. You can see kind of what's going on. Yeah, it would amaze some of you working as interns right now. Maybe you've been out to jobs. I've been out to so many jobs, some of them in litigation where you got serious water problems. And I go to the job and we do a wall cut. And basically this flashing right here that I've got that's going under this block right here and up the wall is on top of the WRB. So the water is just coming down the WRB and running right behind the flashing and then right into the building below. Sometimes it just blows the mind. And I don't mean to sound critical of the construction industry. I'm not. My grandfather was a mason. But it just blows my mind. Sometimes it's so simple. This is from the National Wall and Ceiling Bureau's hard coat stucco manual. It's a great, fantastic concept drawing. Studs, it doesn't have to be wood. Sheathing could be plywood, oriented strand board, or gypsum wall, gypsum product, right? Could be any sheathing. they recommend 2 layers of WRB. You can read about that in their document. Then a metal lath, then attached over that, and then the stucco, the scratch, brown, and finish coats of the stucco assembly. All you can see, here's the weep assembly at the base of the wall. It's tied behind the. It's tied, properly. Its vertical leg properly behind the main WRB, right? Here in America, I don't know what Canada is doing. I just don't practice up there, but work with your Canadian counterparts quite a bit in IIBEC. Here in America, in the 24 building code, it might have come into play in the 21 code. We're on a 3-year cycle here in America. They are adding a drainage mat that will go right here over the so this would be a building wrap WRB right here, right? Which they're calling in this drawing the incidental drainage plane, but you can see that's what laps over the weep, right? Code is going to require very soon, Georgia, where I live, is on the 18 code. They're going to adopt the 24 code in January, this coming January. When that code is adopted, there'll actually be a drain mat added right here. So basically the lath would be over about a 3/8 inch drain mat that's, it lets water, it lets 2 things happen. It lets water drain in that 3/8 inch channel that's over the paper, but it also allows air to go up behind the stucco and dry things out faster. I think it's a fantastic addition to the code. But this is if you're not screenshotting everything, screenshot this, because it shows you the concept, and that's what I want you to get today. This is that's the same exact drawing. This is an isometric view here. This is a section view of the same exact thing. So if you can blow that up, and you can see how everything's shingle lapped, and you can see how the weep assembly works. So basically water is going to get behind the stucco at control joints, at any joint with a dissimilar material. It's going to get in, and then it's going to run down the incidental, they call it the incidental drainage plane in their drawing, but y'all get it. That's the WRB. It's going to run down the WRB. It's going to lap, which is lapped over the flashing, and then weep out here at the bottom. There's actually holes on the underside of this weep that let it drip out the bottom. So I think I've already covered WRB, and I want to get to the photos that we're going to get to. So if you have questions about WRB, then put them up on the chat for Rick to see. I think we've already covered this. Some other basic principles. Caulk is not a waterproofing. In rare cases, it is, but then that requires maybe a double caulk joint. Dow, DOW. Dow has a sealants manual that's like 60 or 70 pages on the details of caulk and its proper installation. It's a fantastic technical guide for you. So, backer rod and sealant, basically proper caulk and installations in situations where the caulk is indeed a water barrier. I would say 95% of the time, caulk is an air barrier. And the principle I want you to remember is the end of this sentence. It will always fail. It will never last forever. So you got to have a maintenance plan for it. It's going to fail. If it fails in most claddings, it's going to allow more air into the assembly. If it fails in a barrier system where the exterior and the caulk are indeed the water barrier, then it's going to cause leaks. So it's got to be maintained either way. Another key principle: windows and doors and any other components that are in a wall assembly themselves leak. So you've got to properly flash the rough openings that those penetrations are in to keep water out of interior space. The ends, the end, we always show a section view like we did there, like we did here. We're looking at section view. You got to think about the end of that view. There needs to be an end dam that turns up, and I'm not going to make you visualize that in your head. So I've got a photo of that coming up. So transition points are important. Say an inside corner, an inside wall corner, or an outside wall corner, you've got to have some extra flashing that wraps, from one side, from one facing wall to the other. So anyway, and then of course, joints. Everything comes on pickup trucks or low boys, right? So, 10-foot length is typically the length of a piece of flashing. So it's got to be lapped. On a 100-foot wall, we're going to have probably 12 pieces of flashing that are lapped. So you got to consider what's going on at the lap joints in a flashing assembly. So anyway, that's just a basic shot of a typical window in a wall. Let's not spend any more time on that. Sill details matter, and I'm starting to move to flashing so you understand how to flash a window. Let's see, we started at 3:30. We've got about 30 minutes left. So I think we're doing pretty good here. So this is why is this bad? Well, you don't see a flashing assembly under this. You see a caulk joint here, caulk joint here. There's no flashing for the rough opening. So if this window system above here leaks in any form, we're either going to trap water between these two sealant joints, which is going to drip into here, or depending on the leak, it may run, this is the exterior right here. It may run to the interior. Typically, there should basically be a flashing under this window system that's lapping over to the exterior or lapping to the WRB back here. So anyway, typical window. This is a trick photo. Anybody, I can't ask you to say anything wrong here. I'll go ahead and tell you. There may be a weep system under this row lock of brick here that I don't have a photo of, that basically the window system is flashed so that it diverts water out weeps that are right below this guy, this row lock. Or there may be weeps that are part of this window system that are blocked by caulk. So the next photo is showing you this is how it should have been done, right? At least from the exterior. So you can see the weep right here that's part of the window system. And then this metal flashing is going up under that. I believe this was on a job I worked on. I took it, but I put it in the slideshow for the benefit of you guys. So there's a weep for the window, but the rough opening has to be properly flashed also, because that caulk joint right there is going to leak one day. And we'll talk about end dams in a second, but if you can imagine what an end dam is, the water is directed to a channel that then it weeps out of here. You can see the flashing here, right? Then there's also a second flashing going under the entire assembly all the way back to the interior, right? But at the ends, if let's say this has just a little slope left, to the left, so water gets in either track. It gets either in the rough opening track, or it gets in the track that's part of the window system. It runs, there's just enough slope that the water runs to the left. Any water that bypasses that weep is going to run right into the interior or the wall assembly. So there's got to be a vertical leg on the inside of the flashing that turns up and is properly sealed so that water, that's what an end dam is. And I've got a good photo of that coming in a minute, so you don't have to, but I want you to capture the concepts here. This is a hard coat stucco, window wall system that we were working on doing some cladding. This is not finished, but we were tying, this was a stone cornice that we were having lots of issues between the window and the stucco. We had leakage under this cornice. So we were in the process of getting a flashing properly to tie all this together. But a lot of assembly components there. This is what I was referring to this would be under a window. This is from Gelled Winds installation instructions, by the way. I've always thought they wrote the best. That's why they're in here. I think they write the best installation instructions. So you can see, here's your rough opening, right, at a window system. You can see there's a back dam. So basically this is one piece of flashing right here, right? The sill pan is going into the horizontal component of the rough opening, right? And so there's our end dam on the left, a back dam on the back, and then the window is going to sit inside this, right? The window in typical commercial construction has its own system, which was just going to just let water out basically where my arrow is here. But the rough opening still has to be waterproofed. So that's a tremendous, look up Gelled Wind and their window installation instructions. It may not be, their current drawing may not be the same as this, but I thought this is a fantastic drawing to show you the concept of an end and back dam. Water gets in here, you're directing it to the exterior with these dams, the end dam and the back dam. You're keeping water in from going to the interior. So this is a similar, you see basically this in this assembly, you'll see this in some commercial construction. Can you follow this flashing right here? Is going up and then forming a back dam. The window is going to go inside of that. So that's a pretty good concept right there for flashing. This is a typical construction joint. You know, you need these about every 30 feet in brick. They're just caulked. Behind that is waterproofing, right? Like we've been talking about. But when those start failing, basically water can overwhelm a water system behind it. So let's talk about air barriers a little bit. And most of my presentation is based on the concept that they're one and the same, but that's not always true. And I've done some work in Ohio years ago where I'll show you. I've got a couple of drawings coming that show what would be more the norm in the northern climates. But basically, air barrier stops air, right? That's why it's called an air barrier. It allows vapor to pass. That's a diffusion issue. We'll talk about that a little bit going forward. So, and this is many times it's one and the same. So it may need to shed water. Tyvek's a great example of a combination. If you're not taking shots of every slide, this is a good one to take slide of, because you can look up Building Science Corporation. I think they're buildingscience.org. Tremendous resource. Their key guy is Joe Stiebrick. He's like a PhD in building science, brilliant man. If you can ever see Joe Stiebrick speak, he'll teach you a lot. But he and his team did a study, this is years ago, where they measured how much moisture movement occurred during a winter season. So this is more geared to the northern climates. So you've got hot, humid air during the winter season. You've got hot and humid air, and look at the typical RH was 40%. That's pretty low RH. So they broke it down. How much of that moisture basically driving from the interior to the exterior? The exterior is cold. This is a heating season. So it's warm and humid inside a home. It's cold and dry outside the home, and water drives from basically air, drives from hot to cold, and airborne, basically air drives from wet to dry, right? Those are fundamentals. So basically you've got differential pressure related to the humidity and temperature differences on each side of a wall. So vapor is going to drive through the gypsum wall board, right? It's going to. So how much during a 6-month period in a 4x8 sheet of gypsum wall board, they were able to, measure this scientifically. 1/3 of a quart through a 4x8 sheet in 6 months is how much water diffused. This is great. Diffused through the wallboard, right? So now but then they imposed on another test area a 1 square inch hole that was not air sealed. And they measured how much water came through that hole. And it was 30 quarts. Blows the mind. That's why, I'm sorry, I accidentally jumped slides. That's why it's so important. That's why air movement is so important. You're going to see as we go forward, you got to, if you have an unsealed hole in an exterior wall or an interior wall that's unsealed and allowing air movement, that air is carrying moisture, and that's going to basically take moisture to the other side of the assembly. And if this has not been thought out, we might have condensation issues. So anyway, diffusion, that's why I told you at the beginning of this program, diffusion is important to understand. And it may be, in some cases, the source of your problem. But often it's the air movement, the uncontrolled air movement is the right way to say it. 30 quarts versus a third of a quart. I always thought this study was powerful. Now you add to that, let's say you got a bunch of leaks in this wall on the left, and now we throw wind at it. The wind's going to push even more. Wind is going to push even more uncontrolled air into the space. If let's assume this is the winter heating season we were just looking at in that prior slide. So we've got hot, humid air where my arrow is, right? We got a prevailing wind. So we got low pressure on this side of the wall. That's going to suck more. That's going to basically suck more air from the interior to the exterior. Say in a cold climate, that could be a big deal. This is a great shot of how does air get into a wall assembly? Well, we might have this could be any exterior penetration, and whoops, doggone it. This could be any interior penetration, right? Or exterior penetration. That could be some kind of vent pipe. Here it's a hose bib, so air is going to leak in here and then find its way maybe to an electrical receptacle or something like that inside. But this you're seeing, this is diffusion through the entire wall cavity. That's very slow and not too much, but the air is going to carry moisture. This is from outside to in this case. So think of a hot, humid time of the year when this is really going to be a problem. Say 90% relative humidity air out here at 90 degrees. That's very typical today. It's 100 degrees outside here in Georgia. So we got high humidity air entering an unsealed airspace and taking unconditioned air into our assemblies and into our interiors. So anyway, I hope I've made the point. So there's another, a view of, you're going to have, remember your wind speeds, when you do design are at 10 meters, right? So a 30 mile an hour wind at 10 meters is typically, 45 mile an hour wind, 10 or 12 stories up. So the higher the building, the greater the wind speeds, and therefore the more air is a problem. Then you have stack effect inside a building, cool air descends. That's an issue during hot climates, but that cool air may be causing something to that can have implications in an uncontrolled airspace, such as think elevator shafts and trash chutes, stairwells, places that might not be properly conditioned. Same thing during the winter. The warm air is going to rise through those same chutes. They're basically they're just places for unconditioned air to travel and wreak havoc somewhere. There's a lot. We're still doing good on our time, but so I'm going to probably go to a lot more photos at this point. Here's a typical attic space concept. I took this photo several years ago. This is the photo. This is what it looked like with flash bulb, right? With the flash on. That's what it looked like. That's what it looked like with the flash off. You can see all the daylight. So basically, I know I've got a lot of air infiltration into my attic space. And yeah, that's pretty normal. The problem at this place, you can see the fasteners from the roof. This owner said, I've got roof leaks everywhere. And I was like, okay. So I went up on his roof. His roof was pristine, didn't have a leak. I was like, there's nothing going on the roof. So I started looking, down below, because he had sealant stains everywhere. I believed him. He's like, it was awful. What he had was, there happens to be some insulation in his picture, but basically his ceiling had about 10% coverage of insulation over the ceiling board. So basically we had, high humidity. This was in Georgia, very high humidity and hot air here, and basically no insulation on top of his ceiling board, an open air plenum attic. And so basically his ceiling panels are probably 70 degrees, and you were hitting a dew point at the grid system holding the ceiling panels in, anywhere. And he had condensation all over the place. That was the problem. This was another case that hopefully drives home the same point. This owner said, we were working on their walls, and they were like, we got a water leak here. And I was like, okay, great. We cut the drywall back, and I was like, look, I mean, his insulation had fallen down, right? So now this is unconditioned airspace here. It did look like a water leak. It looked like a water leak. I cut the flash off. That's the photo. We had an air leak there. There was not water coming through there. As you can see right here, there's no water leakage here, right? I think there's a cladding on the outside, and there's a building wrap on the outside of the cladding. So he did not have water leak. You can see his studs all look good. There's a window right above this, but he did have an air leak. That's with the flash off. So he basically had air. He had air movement from exterior coming to the interior, and this insulation wasn't, stopping the air movement. So basically we had a condensation. Now so you remember, now we got air leakage, right? But if you got a pressurized building, if you got a differential between pressure from outside caused by your HVAC system, the short summary is you can get what I call negative air pressure. And basically let's assume your supply ducts, I'm gonna do this math real easy. Let's assume your supply, your fans are running at 100 CFM, right? But you've got enough leaks in your supply lines that they're only effectively getting 80 CFM to whatever you're doing, right? But the fans are circulating at 100 CFM. The fans at the fan are generating 100 CFM, and you've got a supply system and an exhaust system. So that means your exhaust vents are sucking 100 back to the air handler. They're sucking 100 to the air handler, but because of leaks in your supply system, by the time you get the air to wherever you're trying to get it to, you're only getting 80 there. So what's going to happen? The suction of the 100 is going to pull 20 from wherever it can. So if you've got air leaks in your walls, or air leaks in your ceiling and in your roof, or even air leaks in your floor, you're basically going to be pulling unconditioned air into the assemblies. So pressurized issues is a whole nother world. I've done several hotels, I've done several health facilities where that was the biggest problem. We're basically just sucking unconditioned air into the facility. It looks like water, it looks like bulk water, but it's not. So I'm running a little tight on time, so I want to make sure we get to some other things. This is a map that everything's going to vary just a little bit from climate to climate, depending on where you are. I've put in the International Energy Conservation Code, the 2015 climate zones. That's right out of the code book. This is what is coming in the is out in the 21 and is similar. And you can see they've gone from just temperature zones in 15 to both temperature and moist. So you can see, so we've got, look at how many different, we used to have 7, right? Here's one down in Miami. Here's 7 in the most northern parts of Canada, or I mean, well, this is the States, and then, you know, so you see what's going on now. Look at the complexity of the 6 years later in the energy code that's driving building construction. So now we've gone to, you know, cool and dry, warm and humid, warm and dry. So I mean, the world's about to change. Take a screenshot of this. This is, I spent a lot of time writing this today or rewriting this today. First plane of condensation is basically, I'm going to summarize fast, is basically I've got a surface temperature that's colder than the dew point of the air that's on the exterior of that surface temperature. If they're out of balance, we're going to have condensation on a cold surface. So if we're sucking a bunch of hot, humid air into a wall assembly, doesn't matter which side it's coming from. In the north, it might be coming from the interior. In the south, it might be coming from the exterior in the summer, or in the north interior during the winter. And if we have uncontrolled leakage, we could get condensation in our assembly below. I think that screenshot it and the rest. I want you to understand permeance. That's often referred to as permeability, right? This is various materials, and their perm is basically, I'm going to explain this to you really quickly, but you can see it right down here. So a perm is a grain per hour per foot squared. Okay, and a grain, I put this in the top of the side, a grain of water is approximately 1/7,000th of a gallon. So basically in a plaster wall, we get 15 grains of water per square foot per hour can diffuse through that material. And we just don't have the time. I mean, we spend our careers on this. I'm trying to give it to you in an hour and a half, but hopefully you can start understanding what perms is. If I put a 0 perm material on a wall assembly in the wrong place, I'm going to stop all moisture, and I'm going to fill the space on the interior side of that vapor barrier up with unconditioned air. If I've got something inside that wall assembly that's getting cold, we might have, you know, water in the, you know, basically behind the barrier, and then we've got condensation issues. So what causes it? Well, just natural air. What also causes it? I skipped a slide. What also causes it is drying of construction materials. Doggone it. Drying of construction materials over the early life of a building, you know, bathrooms and kitchens, you know, cooking a lot of pasta. Imagine cooking a lot of pasta and a lot of steam going into the house, or a lot of showers. We just, our normal respiration, HVAC systems we talked about, if there's any issues, especially I put this in here, that's a loaded term there. You might have a common system in, say, a hotel, and you have individual HVAC systems in each room. If they're not properly balanced with each other, you can have issues. Just good old moisture drive. That's basically diffusion through assemblies. So anyway, I'm gonna fly low here. So construction, this is like how many, this is kind of interesting, liters per day. This is for a square foot area of how much basically moisture is in assemblies, you know, that's got to dry. You know, think of concrete masonry unit block or wood that's wet. You put finishes up, it's going to dry to the interior over the first year or two, and you know, it's going to take a while to get to equilibrium moisture content. That moisture turns into basically moisture laden air. So you know, concrete floor. So anyway, these photos are pretty good. I like these both of this photo. This is a floor. This is basically at a vapor drive situation, or a lot of wet concrete got covered by moisture impermeable surface coating, and the moisture's trying to get out from under it. It can't. This is a zero perm material sitting on top. So what do? You get blisters, right? We get blisters on roofs for this, that are bigger than these. This is a 2x2 carpet tiles on top of a concrete floor. I had a case just like this where a school was built. A school about 5-6 years ago was built over the floor of a 1910 concrete floor garage. I know the garage floor, concrete floor, had no vapor management at all under a 1910 garage floor. This is exactly what it looked like under the carpet. They were like, our classrooms smell musty. What's up? And so we came up with a negative side waterproofing to put over the concrete, pull the bad moldy carpet up, put new down, and basically stop the moisture at the top of the slab. This is typical construction down here in the States. I know we've got some Canadian folks. I'm betting you guys are doing a lot of commercial wood frame. So imagine that building right there getting full of water for the next year until they finish it. They get the finishes up. That water's got to go somewhere and dry out. That's got to be considered. The other thing that's got to be considered is this horizontal component. Look at that. That's all water stained right there anyway. But this horizontal component right here is going to shrink during the drying at a greater rate than the vertical elements. And that's causing a boatload of litigation and cladding breakage and all kinds of leakage issues here already. I mean, we worked on jobs over and over where that's an issue. So I put that in so you'd know, pay attention, to what's going on out there. I'm going to fly through these. This is like the average. This shows you how much water gets put in a system. You can screenshot them and look at them later, but that's what a shower does in terms of how much water it puts into the air. Gas cooking versus electric cooking. Pretty fascinating. Yeah, these are National Institute of Building Sciences is our source here, right? I've had mold cases in gyms where we're over here. We got 20 people working out. They're putting that much water in the air at a system. The HVAC can't keep up with it. What does ASHRAE consider normal humidity inside? Somewhere between 40 and 60. This number has been moving. This is an older slide. This is 1989. This might have moved a little bit, but that gets you in the ballpark. If you get into real tough situations, you might get into some high growth thermal modeling. There's multiple softwares available. I don't have them all listed here. Woofy is very expensive, but and requires a little, it's a little complex to run. It was developed by the Oak Ridge National Laboratory, and you can go find it. Woofy, just Google Woofy, and this might have been updated. This is showing you some of this. This is just like sort of like the building science side, but this is out of Woofy. They're looking at how much air movement can come through an uncontrolled opening versus diffusing through the wall, right? Through this wall assembly. And look at the what was amazing to me. That's pretty low relative humidity, and this is pretty low relative humidity too. So this is a winter. This is very similar to the building science. Woofy, the model is showing 1,000 grains per hour, right? So it's 1,000 grains per hour. That's a gallon every 7 hours, right? Versus versus like negligible air vapor movement through the assembly itself. Similar here, but I want to get some pictures. So this is the wall. I was thinking about this slide earlier. So basically in the north, you're going to have a vapor barrier right here. But remember, if that's got to be far north, if you're in the middle, if you got a hot summer and hot, humid summer and a super cold and dry winter, this might really damage you during the summer. So this has got to be thought out. At what point do you add this 6 mil poly on the inside wall, right? This would be stopping your bulk water and your air, typically in the southeast, and that's what the next slide shows. See that here's a southern climate does not put a 6 mil poly there, right? If we did, we'd be trapping water in this assembly for a whole lot of time. I've seen that happen. It's awful. I mean, it was just awful. Y'all can screenshot that slide. I think is driving home the same point. So I'm gonna fly through these photos. How far we're over by about a few minutes. I'm gonna just fly. This is a stucco building, 3 stories, wood frame. Here's your roof to walls. There's a scupper. There's a louver. We got bunches of doors and bunches of handrails. This was the worst job I'm telling you I've seen in my career. This is what brought us to the job. Stucco cracks all over the place. See the cracks here? The reason the stucco was cracking was because there was so much moisture behind the waterproofing was atrocious. This is more of a bulk water job than an air movement job, but there was so much uncontrolled water getting to the wood framing, that the water should never have gotten there, that it was causing the framing to swell. This framing was swelling. The brittle stucco started cracking. That's a pretty good shot. This is what it looked like inside. And by the way, this was 18 months old. So, and it was serious litigation. We worked closely with the general contractor. We were working for the owner. And we fixed this was 10 buildings. We fixed one of them. We did a prototype repair on one of them. It went through 2 hurricanes after our retrofit, before we left the job, and that the building basically didn't leak during 2 hurricanes, but it leaked all the time before the retrofits. But you can see, look at how much damage we had. I can show you thousands of pictures like this. Look at these wall studs right here. That's 18-month-old wall studs. It was just atrocious. Look at that's a long shot, but that basically they're repairing, those are steel posts. They're replacing the structure here because it was so damaged. And those are temporary steel posts during the work. So anyway, that's a closer view. You see the steel basically holding up this corner of the wall while we get all this replaced. It was just a nightmare. I thought these are pretty good IR shots. We did cuts all over the place to figure out what was going on. But remember, we had 10 of these buildings, and they were about a football field and a half times 3 stories. It was a lot of work. So once we got the cuts down, we tied our cuts to infrared. This doesn't always work. This was a non-metallic lav. A metallic lav might have precluded the ability to use infrared technology. But you can see basically we had problems at our floor lines. We had problems at our outside corners. These are really good. We had lots of problems at our terminations between the wall and the balcony. You can see this is an outside. Can you see that's an outside corner? So that's basically just atrocious waterproofing at the outside corner. So water's getting there and then soaking into the wood, So I think these are almost self-evident. Let's see. This, typical waterproofing between the balcony waterproofing and then hitting the wood frame columns. It was a nightmare. It was it was instructive from our world. There's another outside corner, some serious issues going on at the roofs. You can see a little bit of problem going on at the window flashings we were talking about earlier. Most of our problems at the building was these floor lines were atrocious, but we also had just amazing leaks at a lot of scuppers. They're not shown in the scuppers were leaking and then letting water come down to a substandard floor line, and then it was game over. This is another building. This is a hotel I looked at maybe about a year ago. And again, my job was to figure out, we got mold and water. We got mold. That's mainly the issue, and which is caused by water. So what's the source? Well, here's a storefront, typical storefront window, no flashing here, right? No flashing at all under the at the rough opening. So the water's just running to the interior. You see the carpets getting all soaked here. That's an open hole. It's like, if we had a flashing in this rough opening, that hole wouldn't be too problematic. I'd rather not flood the flashing, but we got holes and no flashing. So you can see it's kind of starting to be game over. And then where we did have some fasteners, they're not properly seated. And so that's how water's getting behind essentially the jamb of the window and door system, and then getting to an unflashed opening. This goes to, that's a bulk water problem, right? It's also an air problem if you think about it, but this is what was really driving it. So the next photo is going to be with this guy off. Okay. That's just a vent. And remember, in hotels, those vents are running 24/7. They're continuously running vents, right? So I pop the louver off, right? I'm popping this louver off, and that's the next photo. So the louver was right here. So you see now this vent's running continuously. It's sucking, in theory, the humid air out of the bathroom, is sucking it right out. But guess what? This assembly right here is not sealed and tied to the wall. That's an airspace right there. So not only is it pulling air here, it's now sucking air in the wall cavity. That's pulling air. I can jump around here. Okay, I'm gonna take you back to that slide 1 second, right? So now go back. That's that wall, the bathroom wall is right here on this wall, right? And now there's our vent. There's our vent that's running full time. That is sucking air, but it's not sucking air just from the interior space. It's sucking it from that wall cavity. So it's sucking outside air into the wall cavity, all the way from the exterior wall all the way to here. Because this is, I'm hoping you're following me. If you were in the room, you could be shaking your head. So this is vinyl right here. That's vinyl siding right here. So I've got hot, humid air being sucked into the wall cavity, and that's hot, humid air all the time being sucked to the wall cavity during the winter months. During the summer months. This room is cool, and this is hot, humid air right here. We got mold all over the place. To make it matters worse, this is the attic of the second floor of the same hotel. Do you see the walls right here? So basically the next photo is going to be better. That's one of the walls in the hotel. So not only am I sucking hot air from through the wall cavity to the exterior, I'm also sucking this hot 150-degree air from that's unconditioned in the attic into that wall cavity that's hitting cold surfaces behind the vinyl and causing all kinds of problems. So did they have a mold problem? Oh yeah, you could smell it. It was awful. And then they've also got, uninsulated copper piping. If that's hot water during the summer, it's probably not a big deal. But if that's cold water, that's just going to drip water all over the place. And then you can see it's dripping it right into that's a bathroom area. This is another job altogether. Same thing. We got roof leaks. Went up in the attic, went up on the roof. Yes, they had some problems with the roof, but guess what? The leak that was in the ceiling below here was from this uninsulated. I think that even says cold water. You see the cold water line right there. So it's just not always leak from above. There's another opening and insulation. This is 150-degree 95% relative humidity air 6 months out of the year, hitting this cold refrigerant line and just, taking water everywhere. So this is what I added to the event. Thanks, it's 5:11. I'm a little over, but I think this is important for you to understand as both in your current majors and what you might be dealing with down the road. This is a great photo of thermal imaging. Can you see this? The steel, I mean, this is probably wood frame, and it's probably in a northern climate, but you can basically see we got insulation between the studs, right? But the studs are not the same R value as the insulation. So look at what you see. You can screenshot this. The big idea. This is new code. This is 21 code. 24 code, I think, is going to read the same. And continuous insulation that is uncompressed and continuous across all structural members without thermal bridges. That's so important because continuous insulation, this is the definition of it. No thermal bridges other than fasteners and service openings, right? So the next photo, this is in compliance with that code definition of continuous insulation, because the energy codes are pushing us to increase insulation on the walls. This is going to become a bigger issue as we go forward in the industry. So here's your continuous insulation over a Tyvek system. That's a fastener. That's the only thing here. That's in compliance with code, right? This is a brick veneer wall. This is rock wool right here. Also, just for your bulk water, this is a fluid applied waterproofing system tied to a membrane weep. You see my weep come out of the brick. You see there's it's a good comparison for what we covered very early. Here's your rock wall continuous insulation. There it is close up. So I'm in compliance with code here, right? That's a thermal bridge, but at least it's got insulation on it. And, we can't have none, or we can't attach our wall claddings to walls. This is another view. And you see, I was very impressed with this job. I was working for a general contractor. I was like, y'all are doing a great job. Look how clean this cavity is. Because going back to bulk water, if I've got a bunch of mortar in this assembly, then water that gets to the back of the brick could hit the mortar that you don't see here and run to the wall. That's often an issue. But this is the same building, right? So they've got a build out. This is all going to be brick, and they've got this build out that they're going to put siding on. This is an education building. You see that guy right there? He's the thermal bridge. So I made him a he. This is a blow up. See this? That's a thermal bridge, and this happens to be a steel stud wall. So basically, this girt that's holding the wall board out from the assembly, they've got insulation in this space right here, but they're going to attach wall siding, cementitious like hardy plank out here. So now that steel 3.5 girt right there, you can see there's one there, there's one there. They're attached to the studs. They're attached through the wall to the studs. So basically, I've got a conductive material all the way from the exterior of the building to the interior of the building. That's going to be a huge problem this coming winter. I showed that to the contractor. He wasn't really happy, but I was like, well, that's why he hired me. This is out of a IIBEC interface magazine. I think this is going to be some kind of wall panel assembly. It's not installed. You can see we've got continuous insulation, beautiful thing. That's what the code calls for. But then somebody hung these, steel. This is wrong. This does not meet code. So anyway, I wanted you to be aware of that. There's an article you can look up. It's a fantastic article. Cool roofs. Cool. I initially had this cool roofs in Georgia. I had to examine these two roofs right here in Georgia. This is a wood frame assembly. We had bulk water problems at this roof. But it's also a cool roof. This is in Tybee Island, Georgia. I'm not too worried about this getting too cold. But I want to show you the next photo is the attic space that looks exactly like the attic space under this guy looked just like this. The only difference, you can look up the June 21 Interface magazine, a really nice article about condensation in wood frame attic spaces below cool roofs in cold climates. It was done by Cade Gramowski. She's brilliant. And you'd learn a lot from reading this article. So this is what I look like in Georgia from from bulk water. But this water in Denver, Colorado is condensation, because this is cold air. This is warm air from inside. This would probably happen in Nova Scotia and possibly Ohio too. You got a cold, cool roof, right? It's not black, it's white. So it's reflecting rays. It's much cooler than a dark roof. You got air leaks that get into this space, hotter, humid air from leaks in the ceiling, right? From the unit below hitting this cold surface. Bingo, we got problems. I don't have time for that one, but I want to call your attention to, thermal bridging is now a condensation source, right? Imagine that's not ocean back there, but a snow-capped mountain in Denver. But this construction's identical. Read this article by Cade Gramowski. It'll make you smarter. Do we have cool roofs in Georgia? I said, you know what? Really, we do. See these? I worked on this building for water intrusion. Don't have time to cover the rest of it. That's it, y'all. I appreciate you listening. And I'm open to, if you got questions, you may have sent them by chat to Rick, or we can cut on everybody can cut on their mic. And if you got a question, let's talk about it. We'll go back to a slide. Thanks for listening, y'all. Looking forward to meeting you at BES in Orlando too.
Yeah, I'm not seeing any questions in the chat. So if you guys need a moment, I know it's a lot of materials that Chris was covering. So.
I call this the fire hose drink presentation. So yeah. And I did go over. We started about 5 minutes late, and I've gone over about 20 minutes. So you've hung in there with me pretty well. Any questions? I'm looking forward to meeting all of y'all in Orlando.
I have one quick question about the pooling on the roof.
Yes.
I was just curious if do the structural engineers account for some of that to happen, or is it expected to be designed to?
They account for a little of it to happen, but they don't count on it. I mean, if you think about ponding failure, my background before I was in enclosures was had an element of structural in it. So here's how ponding failures occur. You pond water, right? You pond water. Well, let me back up. There's deflection. There's always deflection. Let's just go to this guy, because this was a roof truss. This system is a roof truss system. This is falling from here to there. It's running from, let's call that the front of the building to the rear of the building. There's about a 112 pitch here. And then there's beams going left to right, right? And then there's trusses going front to rear, okay? Which that would be a front to rear truss, right? So let's assume that there's well, let me back up. So there's probably somewhere along, let's just use these penetration lines that's probably a beam support or a truss support going left to right, and a truss is going front to rear. I'm hoping you're following me. So there's natural deflection. There's already deflection in the member that's going front to rear here. There's already some deflection in it. So that needs to be considered also, because where you set your drains, you may be setting your drains where natural deflection and I would say code allowed deflection. The building roofs are typically allowed to to deflect about a 1/2 inch in, let's see, it's L over 180. So yeah, that's 1 inch in 15 feet. So you're already allowed by code for that truss from, lost my arrow, from here to here to deflect. So that's got to be built into the drainage system. But what happens, let's assume you have an uncontrolled pond. So, and I get water in, I've got a drainage issue. This is how roof collapses happen. So I've got a drainage issue somewhere, and I've got a secondary drainage. You're supposed to have two modes of independent drainage on a roof, right? Let's assume they both fail, or let's assume that the secondary drainage didn't get put in, which I can tell you that I've seen that a lot in my career. You get up on a roof, go, hey, y'all don't have any secondary drainage up here. But let's not get into too much detail, as I've already done already. So basically, a drain gets plugged somewhere, right? I've already got 1 inch and 15 feet allowable deflection. But now that with a drain, clogged somewhere, I start to get 2 inches and 15 feet. So I basically I start overloading the structure. And what happens is the more load you put on a pond, the more deflection you get from the structural element. Go back to here. I know it's at the end of the wall, but just imagine him going 20 feet behind us. The more load I put on this beam, well, doggone it. The more load I put on this beam right here, and remember, we're seeing about 2 feet of that beam, right? The more load I put on him, the more he deflects. So the more he deflects, the more ponding he can take, and therefore the more he deflects. And it's like, that's why they call them ponding failures. So basically what happens is a pond develops, it deflects the beam, which creates a bigger pond, which water can flow to, which creates more deflection until this guy right here says, I can't hold on anymore. And that's how collapses happen. I hope I answered the question. And if I didn't, ask a follow-up.
No, I think I got it cleared up enough. Thank you.
It's really, that's why drainage is important. I told you during the beginning, don't ever put an insert in a drain assembly, because you're basically going to create new ponding on the roof, which it might not have been designed for. And if you find a roof that doesn't have secondary independent drainage, independent of the primary system, if the primary system gets clogged, then there's a potential for game over. And I sound sensationalist, and I don't mean to be. It takes it goes back to, it would probably take about a 4-inch load of water or a 5-inch load of water on this roof for it to collapse, because the design typically for the roof structurally is a dead load of whatever the material on it is, HVACs, they figure all that out. The structural engineers figure all that out. The dead load of the dead weight of the materials, the dead load, plus typically a 20 pound per square foot live load. So it's got a live load design, right? But if we get, this is like about a 3-foot parapet. If I get a clog in my drainage system, and I get above 4 inches of water, 4 inches of water is 20 pounds per square foot, 5 pounds per square foot per inch. So if I get more than 4 inches, I'm probably going to start over deflecting the trusses, because they're designed for 20. And then it's back to they're not just called ponding fails, uncontrolled ponding. There's nowhere for the water to go but to stay in the pond. And the more that falls in it, the more deflection you get until something breaks. That's a very fast discussion. There's some great articles on that too. Maybe look up uncontrolled ponding failure and maybe put plus structural or something, and you'll see some excellent, articles to help you get smarter there.
Thank you. I'll have to look that up.
Definitely, Mac. Look forward to meeting you. Go Buckeyes.
Go Bucks.
All right. Well, listen, everybody. I'm going to go ahead and schedule another follow-up just for general questions for people, and have Alec Jeffrey join us, and that will be in September, closer to the BES. But if you have any questions meantime, feel free to reach out to me. There are a few of you, I still need your flight information so we can confirm your hotel and get all that nailed down. So thank you so much, Chris. Folks,
Enjoy.
have I guess tomorrow isn't the weekend yet, but enjoy the rest of your week. Okay. Thanks, everyone.